My name's Jeff Harris, and I've been working with Metal Earth for the last couple of years, heading the data analytics group. So we're going to change gears a little bit and now do something completely different, as Monty Pythons would state. We're going to get into the world of AI and machine learning language. This is nothing new. I've been doing this stuff since 1990, so it's really caught on recently. And I just want to caution you that AI has a place in our geological toolbox, but it's not the end all to be all, obviously. So we got to treat it with a little bit of grain of salt. It's very popular now, and lots of firms are providing courses on this sort of technology. But let's think geology first and AI second. So I have to thank Lynn for my opening slide. She made it look much, much better. Thank you, Lynn. So I appreciate that. So the team members, I've listed here, they're all contributing co-authors to this talk. I have to thank Ross for supporting all our activities. He's been great with funding our activities and helping put our team together. So there's Ross, there's myself, there's Eric Grunsky, there's Paran Bienya, Mustafa Nagazeta, and Anbar, and we have a new person coming on who's actually here now in Sudbury, Ahmad, and he'll be joining our group in a few weeks. So the objectives, obviously the objective of Metal Earth is to fertile versus barren belts. And one way we can approach this, as I stated last year, was through mineral potential modeling or mineral prospectivity modeling. That's where we integrate all the data and produce some sort of map or idea of where to look for the commodity of interest. Now, would I say they're target maps? No, I wouldn't say they're target maps. I just think they're narrowing down the area for exploration, for follow-up work on the ground. So let's be clear on that. Just to review, we've completed most of the transects with mineral prospectivity maps. Noranda, Swayze, Larder Lake, Chibougamau, Geraldton, Rainy River, Sturgeon. We're working on a project now comparing Matheson to Dryden. Malartic is being run by Paran Bienya. She's going to start some work on that where she's comparing different machine learning algorithms to see what gives us the best results. We're not sure what's happening with Anacocan and Sudbury at this point in time, but we've made good progress in producing mineral prospectivity maps. This is just a list of papers that have been published, and the ones in red at the bottom is we've just submitted a paper with Bruno on the Geraldton area, and that was being submitted to World Geology Reviews. And I'm recently working on a multi-co-author project where I'm comparing Matheson to Dryden. So Matheson is fertile, Dryden is less fertile. So we're really trying to stick on the theme of fertile versus barren. So if you're interested in any of these, you can get them through the literature or talk to me. We also are developing a new geochemistry project. This is being led and initiated by Eric Grunsky. And he talked about it yesterday in a fair amount of detail. So Eric is with us today. So if you're interested in that particular project, then you can talk to Eric after the talk. This is what has been compiled so far in green dots. This has been done by Paran Bienya. And this will be the basis of this new project. It's going to be a standardized data set with which industry can use. It's going to have the same imputation methods, the same analysis. So it's going to be a really great data set once we get through with it. So thank you, Eric. We also, as Ross said yesterday, we have the website fully up and going. There's the URL to it. And I encourage you to dig into this website and try to download some data. Anbar and Paran Bienya have worked really diligently on this task, and I think it's a really good website. I've been on it and downloaded data, and it works. So that's a major goal for us in the data analytics group, thanks to Ross, is making sure this data is available to the public, including industry. So basically, this shows all the areas that are now compiled on the website. The only ones we haven't compiled is Atikokan and Sudbury, but all the rest are available, both in the Abitibi and Wabigoon. So that's a bit of a review. What I'd like to do now is just give you some very preliminary results on a multi-authored paper that I'm leading, comparing Dryden, which is not fertile, basically, versus Matheson, which is considered more fertile. So you can see Matheson is here, if you follow the cursor, and Dryden is here. So the geology for Dryden comes from Rebecca Monsiome et al., and Stefan, I think, had a lot to do with this work as well. Published a great paper recently outlining the differences between Dryden and Matheson, and I'm continuing that work. So this is just a geology map. I bring your attention to these deformation zones that have been mapped. They may be important. Here's the map for Matheson. You can see we have a band of metasediments, the major faults, Porcupine-Dester, and Pipestone Fault. These become very important in the gold story. What I've plotted here in these white stars is just the gold mines. And you can obviously see a spatial correlation between the major faults and where the gold mines lie. So I just provide this slide to put mineral prospectivity mapping in an overall process. We start with a deposit model. In this case, what I'm showing in Dryden and Matheson is based on orogenic gold. So we have to know what we're looking for, because this tells us what vectors we can extract from our GIS database, be it QGIS, be it ArcInfo. And we select vectors to mineralization that we call evidence maps, and they can be in various formats, binary, multiclass, and continuous. And then we are faced with choosing a machine learning language algorithm, and in this case today I select random forest because I think it's one of the most powerful algorithms out there for doing this sort of work, and I'll show you a chart on that in a minute. And then once we produce our model, it can look beautiful in terms of range of colors. It can impress our management, if you like, but we have to validate our model, and that becomes a very important process. How well is our model performing? And we use classification metrics, efficiency of classification curves, and rock plots, which I'll talk about shortly. So here's the distribution of gold in Dryden and Matheson. And it turns out with random forest, what we're looking at is the presence or absence of gold mines, prospects, or occurrences. But we also have to have a random data set, which we call non-deposits. And that's shown in green. You can see that quite clearly here in both areas. So those are the two classes we're trying to model, is where it's prospective for gold, based on all our integration of our evidence maps, and secondly, where it's not prospective. So here's a list of evidence maps, and I'm not going to go through them all, that we used for Dryden and Matheson. Now I do point out there's structural variables, there's geochemical variables, geophysical variables. But one thing we had in Dryden was a very dense lake sediment geochemistry, so we decided to use that. Now, Eric may have some comments on that, and we'll discuss that later. So. And we had lithogeochemical data, but it wasn't always dense enough in terms of samples to work with. And it turns out, long story short, that the lithogeochemistry wasn't as predictive as we had liked it to be, hoped it to be. And that's probably because of the distribution of samples. There was a paucity of samples. And this determines whether we interpolate the data or we come up with some other method to look at the zone of influence around. So I'll mention that. So random forest, I'm not going to go explain through this in detail because we did this last year, but it consists of a forest of trees, and down each tree we take our training area, which is our gold prospects, our gold occurrences, more importantly our gold mines, and we take 2/3 of them for putting down each tree, and we leave 1/3 as a separate entity used for testing and calculating what we call an out-of-bag error, and I'll get to that momentarily. And that, in machine language parlance, is known as bootstrapping. Yes, we have in machine learning, we have all these fancy terms to mean various things, just like geology. So, and then what we do, that's the first reason for random, calling it random forest. We employ bagging, which is we don't put all our evidence maps down each tree. We put a proportion, and usually it's a square root of the number of evidence maps that we have, and that's been proven empirically to be a good number to put down. And so our final map is based on the evidence from all our trees. We take a majority vote at a given area in a raster model. It's a pixel. And we take a vote to see whether it voted for gold, prospective for gold, or not prospective. And we actually calculate here a probability. And this is what I use for mineral prospectivity mapping, the probability map. And this is the way it's calculated. The other advantage is permutation importance. What are our most important predictors for exploration? And this explains it here. If anybody would like a copy of this presentation, I believe it will be online. Ross, these presentations, will they be online? Oh, I'm being video. Oh my God. That's hideous. Stay away, Kramer. I'm hideous. Anyways, the thing is, it gives a idea of what our most important predictors are. It gives us the most important predictors, but what it does not say anything is about processes. Up to us to figure, well, what process is being operational? Why is this predictor important? What's the process behind it? And my next project after the Dryden Matheson project will be to compare all the predictors across the Abitibi and Wabigoon to see if we can extract any reasons why there are differences in the predictors related to processes, and then determine some conclusions about Wabigoon versus Matheson. Our validation, I just put this hypothetical example of validation where we plot on the x-axis our area of prospectivity map from high prospectivity down to lower prospectivity, and the number of gold occurrences, either an absolute number or in percent predicted. So normally we're looking for a curve that is shaped like this, because what it's telling us is 100% of the gold points are predicted in 10% of the area. So that really reduces the amount of area for exploration when we go out in the field to check out some of these zones. Also, with the mineral prospectivity map, we're interested in predicting the known gold training areas, prospects, mines, whatever. But we're also interested in identifying areas that do not have any gold occurrences as being prospective. So there's two reasons for the mineral prospective map. So here's a mineral prospectivity map of Dryden and two of Matheson. Of Dryden, I used all the gold data because there just wasn't enough to divide it into mines and prospects. There was just too few to get a robust model. Whereas in Matheson, there were a lot more gold occurrences. So this map is just based on gold occurrences, or gold mines, if you like. So this becomes more important because obviously we think the mines are the most important. And we can weight the mines on tonnage, if you like, which I've done in a previous paper with Bruno in looking at Geraldton. And the map on the right here is based on all the gold data. And immediately you can see the effects of the major faults here. And this is quite a bit different from what we see in Dryden. And we see, I've mapped the faults or plotted the faults on top. So obviously the spatial association between the gold and major faults is not rocket science. You can see that visually. And of course, the random forest picks that up statistically very well. But I also bring the zones here and here as being very prospective. And perhaps the reason of that is Jorgi gave a good presentation in our gold workshop that we had on Wednesday, and she maintained that cross faults are important. So here we can see there's lots of cross faults in this area where a lot of the gold occurrences are. In fact, I completed a study of faults across the Wabigoon and Abitibi and found that one of the best predictors was the intersection between cross faults, northeast trending cross faults, and east-west trending major breaks. So that's what the probability map. So areas of higher probability for gold exploration are in warmer colors, and the cooler colors represent areas that are less prospective, and of course they represent, in some cases, the granitoids. So let's look at the metrics of what we've done here. The out-of-bag error is defined by taking the samples that we did not put down each tree, we put them down the tree and measure our what's called out-of-bag error. And you can see these are in the 70s. This precludes, normally in artificial intelligence operations with machine language learning algorithms, we keep a test data set separate, a test data set of gold. And we measure the classification metrics based on these samples that weren't even used for any sort of the modeling. Well, random forest actually incorporates that through boosting, which I explained earlier, because it doesn't use all the samples for each tree. The best predictors, very interestingly enough here, to summarize briefly, is that the density at fairly deep levels becomes very important. And we can see that why that is in Matheson. But in both areas it becomes very important. But what the big difference is the location of contexts and faults in Matheson seems to be much higher predictors than what we have in Dryden. And is that telling us something about, is there a difference in the gold deposition model? These are the efficiency of classification curves, and this is for Dryden. We can see this banana-shaped curve. So 87%, I can't read this, 82% of the gold is predicted in about 20% of the area. So we have reduced our area for exploration. In these curves here, they're all good results. They're all area under the curve, which is basically a measure of how well it's done, the model is done, are all above 9. But it's interesting because what I did was look at the mines versus the mines, the prospects versus the prospects, and the occurrences versus everything else, all the points. And these are the curves that you see for those. The curves here are generally not very good, not a very robust model, because we're cross-comparing. For example, what I mean by cross-comparing is we're looking at mines versus prospects, predicting prospects. Prospects predicting occurrences. But the straight line from here to here means that our model is no better than random. So I would throw away this data here. It's not very robust, not very good. Here's just an example of some of the evident maps that are important for predictors. You can see density, and I've overlaid the faults and contacts. This low density zone is metasediments. So whether it's high or low, it's still predictive because it's a low density. Does that have anything to do with the source of gold in relation to the position of the major faults here? I'm not sure. And then we have the major faults that I've buffered as a zone of influence to 1 kilometer. And you can see I've overlaid the mines again. You can see a very good correlation with the Destor-Porcupine fault. Here's the best predictors for evidence maps for Dryden. And the lake sediments for gold and arsenic were actually by drainage basin, compiled by drainage basin, were actually quite predictive. So Eric and I will have to continue that, that discussion, right? So what I did in this slide is I took the top percentage of the predictor maps. In this case, it was 32 evidence maps that I modeled using random forest. And I selected greater than 0.8 probability. And I came up with these zones here. Here, and here, and here. So this is interesting because you can see the curvilinear occurrence of gold up here, and that means our model is performing pretty well. Whether this big intrusion here has anything to do with the deposition of gold as a heat engine, perhaps, is a moot point. It's up for debate. And the same thing here with B. You can see this zone does correlate with some high deformation zones mapped by Becky. This doesn't correlate with any deformation zones, but it is related to, perhaps related to this intrusive here, which may be in a heap source. I know that we've got to consider age, et cetera, timing of gold, but I'm just making some observations based on what I see in the data. And then down here, this is mainly in mafic mafic rocks, intermediate and mafic. And then we predict the, I think it's the Goldland mine pretty well up here. The Goliath mine is here, and we don't predict that too well, which is probably not good. Looking at Matheson, you can obviously see the effect of faults here, the major breaks. And again, at the end, where we have cross faults. And maybe that has a role in the gold model. Maybe displays cross faults house some of the gold. I think it was Francois Robert in one of his papers some time ago noticed the importance of splay faults. I'm not sure if it was you or Howard Paulson. Yeah. Yeah. So that seems to support that. But we do have lots of zones down in the south. And I didn't put the faults on this, but they seem to be associated with north trending faults and fairly close to intrusions. If you think back to the geology map, I should have put the contacts on here, but is something different happening south versus the sediments in relation to the major faults here in terms of source of gold or traps? It's up for discussion. Now I'm taking the liberty to do some arm waving. I like to call it educated observations, let's put it that way. So this is 3D MT seismic image of Matheson, and I believe Rasmus Haggard had a lot to do with the interpretation here. I think this was published by Ras, and it's a very good publication. Versus Dryden, and this is, I think, done by Stefan and Becky. Now, this is not looking at the cross sections or images that have been color standardized. And John is leading a project that we learned about the other day and looking at an atlas of all these types of images. So this is on the non-colorized, but I think it shows some interesting results. I think it shows that there are more conductive zones that seem to reach the surface that correlate with fairly large faults. You can see here, in here too, and where the crust seems to be more resistive in Dryden. Is that important? Well, these are just observations I'm making from the data, so it's something we have to consider in our fertile versus barren story. So I took the liberty as part of John's project and looking at the atlas of comparing all these images across the Wabigoon and Abitibi. And here's some of the things, the observations I've made, and you can read them for yourself. Doing with more resistive crust, more conductivity zones coming to the surface, correlating with steeper, deeper faults, as opposed to more listric faults in the Wabigoon. Perhaps this will tell us a story that we can help determine fertile versus barren. Now, I should go back to this and just say, in our gold discussion group, we had a discussion about, well, this is showing us what it's like now in present-day environment. We had a discussion, a little bit of discussion about that this morning. Well, what about, does this represent really what was happening in the Archean? I don't know the answers to that. We have to rely on our MT experts like Dave Snyder and others to address that. The other thing that came out of the gold meeting that I thought was a really neat idea, and it came from Francois Robert, was the degree of preservation in the Abitibi versus the Wabigoon. Maybe that has something to do with it, the story. Bruno has told us that the grade of metamorphism is higher, at least in the eastern Wabigoon. Could this mean that more of the higher degree of erosion and thus taking out a lot of the gold versus the Wabigoon? Interesting theory. I'll let the experts follow that one up, but that's something else we could consider in the fertile versus barren story. So just in summary, we've published and worked on a lot of transects. We've got a new exciting geochemistry project initiated by Eric Grunsky. We've made some observations as part of the Atlas program on the MT and seismic interpretations. Our web delivery system is almost complete now, and it's up and running and very well. And we have a new hire from Iran coming in March, and we'll be getting him to work on more studies relating the conductivity zones to the position of gold, and that was Dave Snyder's idea from last year. So we're going to get him to work on that across the Wabigoon and across Abitibi. And he's a geochemist by trade, so perhaps we'll get him to help in the geochemistry project. That's all I've got to say. Thank you.